So, dear students, I welcome you for the today's lecture related to the scale up of agitated vessels. Now, scale up and scale down. That means we are having the small or the prototypes that is used in case of our laboratory. Generally, we perform our experiments in the laboratory and then we try to scale up from laboratory to the pilot scale and from pilot scale to the industrial scale. That means the production that has to be increased from a very small volume to a volume of say 5 liters to 100 liters in the pilot scale, and from thereafter to the large scale, that is in terms of the 1000 liters capacities in terms of the production scale or industrial scale. So from laboratory scale to pilot scale and then to the industrial scale. So this is the scale up. Sometimes the scale down, that is also there, from industrial scale to the laboratory scale also. But it's generally the scale up that is there. So for the optimum design, so whatever the results I have obtained in case of a laboratory, the same results that should be reproducible in terms of your production scale. So one has to correlate the different parameters in terms of the geometric similarity and the dynamic similarity, which will be providing me the resultant output similar to that of the laboratory scale products. So for this, the optimum design of a product scale, say for example, the fermentation system, which is the prototype, the data on a small scale, that is the model, must be translated to a large scale. So this fundamental requirement for scale up is that the model and the prototype should be the similar to each other. That is the basic need, basic purpose. Then and only then you will get the desired output or the required output. So two kinds of conditions must satisfy to ensure this similarity between the model and the prototype or the industrial scale. That is, one is your geometric similarity of the physical boundaries, and second is the dynamic similarity of the flow fields. So these two similarities, one is the geometric similarity related to physical boundaries. That means the dimensions, length, diameter of the vessel, height of the liquid. So this is the basic diameter and the height, that is your geometric similarity. Diameter of the impeller. Then the dynamic similarity of the flow fields, that will correspond to the developed flow patterns. This is depending on the speed of rotation, how the fluid that will be rotated, how the buffers that will be available. So these are your dynamic similarities, the flow behavior, how the fluid that is moving, that is the dynamic requirement, that is dynamic similarity. Then this geometric similarity of physical boundary, that is same type of a reactor one is going to use it. Simple batch type reactor we are going to scale up generally. Then all linear dimensions of the model must be related to the corresponding dimensions of the prototype by a constant scale up factor. So we have to first calculate the scale up factor for this purpose. This scale up factor that will be helpful for correlating the smaller dimensions to the higher dimensions. So all linear dimensions of the model must be related to the corresponding dimensions of the prototype. That is, keep the ratio to the height to the tank diameter same, h upon dt, that is kept as the constant, that is L upon D, h upon D or h upon dt. So length is nothing but your height. So that corresponds to say 2 to 3, that will be there. Now consider an example. This example, that is 2-liter vessel. So it's a model. 2 liter is a small vessel which we can perform it in the laboratory, and that has to be scaled up to the 2000 liter. From a small size of 2-liter vessel, we have increased it to the 2000-liter vessel for the industrial scale prototype. That is, prototype is nothing but your industrial scale. Model type is nothing but your laboratory purpose. So this fermenter by a geometrical similarity. So this is the case related to the geometrical similarity where h upon dt, which is given, equals to the t. Then the impeller diameter di, which is equal to the 3.24 centimeter. Then what must be the dimensions of the model? That is height of the model, then diameter of the tank, and what is the diameter of the tank for the model, and the prototype, that is the height of the prototype, then diameter of the tank for the prototype, and diameter of the impeller for the prototype. So this is the data that is provided. That is from 2 liter to 200 liter, and diameter of the impeller for the model, that is given as 3.24 meter, and you have to calculate the height of the model as well as the diameter of the tank of the model. So generally it's a volume, that is nothing but pi by 4 d square into the h. This is our basic formula for calculation the volume. That is pi by 4 d square into the h. However, in this numerical, that is mentioned as h upon dt, which is equal to the 2. So h will be is equal to 2 times dt. This is the calculation m that corresponds to the model. So Vm, that corresponds to the volume of the model, that is nothing but pi by 4 into diameter of the tank of the model into the height, where the height of the model, which is equal to the 2 times the diameter of the tank of the model. So I can substitute these values of the h in this and can write in terms of the d. So volume of the model, which is equal to pi by 2 into the dtm cube. Then diameter of the tank, which is correlation we have obtained, that is pi by 2 dt cube into the tm. So simplification of this and substituting the volume of the model, that is from 2 liters. So it becomes 2 into 2, that corresponds to the 10.8 centimeter diameter of the tank. That corresponds to the 10.8 centimeter. And the diameter of the tank, that will be equals to the 2 times the height of the tank will be equal to 2 times the diameter, so it becomes 21.6 meter. Now these are the all calculations corresponding to the model, that is a laboratory scale. Now on the basis of similarity, on the basis of similarity, I have to now develop a prototype or an industrial scale. So this is the basic data which is available in terms of a laboratory. Laboratory का data है, तो that is given, that is corresponding to the volume, the height to tank diameter ratio, and the diameter of the impeller. The three things has been given. So from there we have calculated the diameter of the tank, the height of the tank. So this is the height diameter of the tank 10.8 centimeter, and the height of the tank, that is 21.6 centimeter. Now based on the similarity pattern, we are going to consider it in terms of the prototype, that is the industrial scale. So pi by 2 into the dt cube of the prototype now. Now this is all replaced, m is replaced with the p, that is prototype. So diameter of the tank for the prototype will be is equal to 2 times the volume of the prototype upon pi. We are knowing the volume of the prototype, that is from 2 liters we have to go to the 2000 liters. So the relationship, that is your scalar factor, this equation, that is nothing but the dTp, which is equal to 2Vp upon pi raised to the 1/3, and this equation, that is dTm, which is equal to the 2Vm upon pi raised to the 1/3. They have been equated. So that I will get a ratio of dTp upon dTm, which is equal to Vp upon Vm raised to the 1/3. So this is the scalar factor that corresponds to the volume of the prototype in terms of the diameter of the tank. So that scalar factor that comes as the 10 now. So diameter of the tank for the prototype is equal to 10 times the diameter of the tank in the model, that comes as 108 centimeter. Similarly, diameter of the impeller in the prototype will be equal to 10 times the diameter of the impeller of the model, that corresponds to the 324 centimeter, 32.4 centimeters. Then the height of the prototype, that will be equals to the 10 times the height of the in the model, so that corresponds to the 216 centimeters. So that the HP height upon the diameter of the prototype, that will be equals to the 2. So this is related to the physical similarity or the physical boundaries, scale up corresponding to the physical boundaries. So this scale up factor is dTp upon dTm, which is equal to V rho upon Vm raised to 1/3. Now the next is the dynamic similarity corresponds to the flow field. To achieve this dynamic similarity in a stirred tank reactor, the dimensionless numbers for the prototype and the model should be equal. So again, you require the different number, that is your power number, Froude number, and the Reynolds number. So the same numbers, the three numbers, that will be going to give you the dynamic similarity corresponding to the power requirement. So P0 is the energy input in the watts, N is in the speed rotation, and the rho is the density kgs per meter cube. Then Di is the impeller diameter in terms of the meter, that is 30 to 40% of the diameter of the tank Di. Then mu is the viscosity, and G is the acceleration due to gravity that will be there. So when it is difficult to satisfy the dynamic similarity when more than one dimensionless groups are involved. Now in this case, the three dimensionless groups, that is your power number, Reynolds number, and Froude number, these are the three dimensionless groups, they are there. So it is difficult. Now say the rho, that corresponds to power number as well as that corresponds to the Reynolds number. The speed of rotation, that corresponds to the power number, Reynolds number, as well as the Froude number. So these are the repetition of the parameter that is there, and as a result, it is very difficult to satisfy the dynamic similarity when more than one dimensionless group that is involved. So design criteria, the constant power input, that is P0 upon V, that is your power number, P0 upon V, or the constant liquid circulation rate inside the reactor. See, constant liquid circulation, that is the fluid which is getting rotated, that is Q upon V, that is the pumping rate of the impeller per unit volume. Then the constant impeller tip speed, that is N into the Di, is the constant impeller tip speed. Then the constant Reynolds number that will be there, that is the D square N rho upon mu, that will be there, and V is your nothing but the working volume. Now in this scale up, generally any of the above criteria should be met, and should satisfy to give you the resultant output. Uh, so scale up, that is generally any of the above criteria should be met with the geometric similarity boundaries. So when you talk geometric similarity, that is power number will corresponding to the n cube into diameter raised to the power 5, diameter of the agitator or the impeller. Then volume corresponds to the diameter cube, and the volumetric flow rate corresponds to the n into diameter cube. So this is the design criteria, that is the constant power input, that is P upon V, that will correspond to the N cube into the di raised to the power 5 upon di cube, which is going to give you the N cube di raised to the 2. Similarly, the constant liquid circulation rate, that will be also there, that is Q upon V, that is Q upon V, this Q upon V, that will be corresponding to the N only, n di cube upon di cube, which is equal to the N. The next is the constant impeller tip speed. Impeller tip speed, that is nothing but N into the di, speed of rotation, N into the di. So this is the uh, we know the Reynolds number in while flowing through the fluid, that is du rho upon mu. However, in the case of agitation, this Reynolds number is di square into the n. Now di square, instead of du rho upon mu, it becomes di square n rho upon mu. So this modification of n into the di, that will give me the movement of the fluid, that is the constant impeller tip speed, that is nothing but n into the di. Then this constant Reynolds number, which is equal to n into di square, since di is directly proportional to dt, the above relationship is also valid for the dt. Then the scale up of a stir tank reactor, the design calculations are we will consider now. Their dp, diameter of the prototype, upon the diameter of the impeller. So calculate the dimensions of the prototype, that is the height, tank diameter, impeller diameter, by multiplying that of the model with a scale up factor. Then select certain the criteria related to the dynamic properties and keep the constant in both the model and the prototype. So here we have to select certain criteria related to the dynamic properties, because this whenever we talk the dynamic properties, then as there are three numbers, that is Reynolds number, Prandtl number, and Freund number, so it becomes more and more difficult for the parameters to follow this dynamic similarity, because the different terms that is involved everywhere. So determine the parameters such as the impeller speed for the scale up reactor. Now we will see this numerical, the same numerical with the dynamic similarity. The same vessel, 2-liter vessel volume, is scaled up to the 2000 liter volume for the fermenter H upon dt, that corresponds to the model, which is equal to the 2, and the impeller diameter dim, which is equal to 3.24 centimeter, and that of the impeller speed is Newton meter is 500 rpm. What is the impeller speed of a larger reactor for constant impeller tip speed and constant Reynolds number? So one by one we will talk. The scalar factor dTp upon dt, that is the ratio of the diameter of the prototype to the diameter of tank diameter in the model type. So that corresponds to the volume of the prototype upon volume of the tank diameter. And that you are getting this is equals to the 2000 upon 2 raised to the 1/3, which is nothing but D10. Then this diameter of the tank is 10 times the diameter of the tank of model, that corresponds to 108, and then 216 is the height. Then for constant impeller tip speed, you will require the speed of the model multiplied by the diameter tank model of the tank diameter of the model, which is equal to the np, that is the corresponding actual speed. So np into the dtp, np which is equal to the nm into the dtm upon the dtp, which is 500 into 10 to 10.8 upon 108. Then for the constant Reynolds number, you will have the n into the dt square. So this corresponds to the n into dt m square, which is equal to nothing but n into the rho into the dtp square. So speed of rotation for the prototype, that becomes equals to the 5 rpm. This is by considering the scale up factor. So this is again the revision corresponding to the scale up laboratory size pilot plant, that is the V1, which is equal to pi into the dt1 raised to the 4. This is talk in terms of the V1 and V2 ratios. So V2 upon V1, that corresponds to the dt2 upon dt1 raised to the 1/3. So this is the scale up ratio R, which is equal to V2 upon V1 raised to the 1/3, which is equal to the dt2 upon dt1. So similarly, the speed of rotation, that will be n2, which is equal to the n1 into 1 upon r raised to the n, which is equal to n into dt1 upon dt2, that will be there.